Firstly, I would like to thank Indonesian Journal of Electrical Engineering and Computer Science to accepting the journal and providing an opportunity to present the paper entitled on high gain circularly polarized metasurface antenna for NR257 band millimeter wave 5G communication. The paper is presented by Mr. Praveen Haandi Lakshman. The corresponding author is Mr. Praveen Haandi Lakshman, working as assistant professor in the Department of Electronics and Communication Engineering, Sri Dharmasthala Manjunatheshwara Institute of Technology, Ujre, Karnataka, India, affiliated to Vishveshwaraya Technological University, Belagavi, Karnataka, India. And this is the abstract of the paper. A metasurface inspired circularly polarized compact patch antenna with high gain for fifth generation communication system is designed and implemented in this article by using a metasurface of 3x3 periodic double-sided identical circular metallic patches, which is mainly used to minimize the impact of scattering and edge diffraction at millimeter wave frequencies, and the overall dimension of the antenna is 1.1 lambda naught into 1.1 lambda naught into 0.2 lambda naught with a peak gain of 11.5 dBic and a 3 dB axial ratio, bandwidth of 28.45 to 28.88 gigahertz, and having an impedance matching and radiation efficiency over a frequency range of 28.23 to 30.01 gigahertz. The proposed antenna design could be well suited for millimeter wave communication systems in scenarios requiring robust long-range performance and high data throughput. Introduction. The significant increase in annual data traffic is projected to require high capacity, improved reliability, greater velocity, reduced latency, and extensive connectivity. Fifth generation wireless communication network is the essential answer to address the aforementioned difficulties and facilitate potential application. 5G communication is standardized into two frequency band. One band operates below 6 gigahertz known as sub 6 gigahertz band, while the other one is millimeter wave band. The N257 band, often known as 28 gigahertz, is being standardized by majority of the countries for their 5G communication. High gain antennas help millimeter wave communication systems overcome challenges posed by atmospheric attenuation and propagation losses, which can negatively impact signal strength. Antennas with circular polarization are favored owing to their increased immunity to interference, losses caused by misalignment, multipath fading, and Faraday's rotation. Microstrip patches are employed in the construction of CP antennas because of their advantageous characteristics, including structure, cost effectiveness, and ease of integration. Obtaining high gain and CP is a challenging when using conventional microstrip antennas. The enhancement of antenna gain for millimeter wave system is needed to improve the communication over long range distances, which has led researchers to employ a variety of strategies, including stacking approaches, array formation, superstrate technique, substrate integrated waveguide approaches, and many more. Metasurface technique is used in this study to enhance the gain so that path losses can be reduced in millimeter waves, which enables higher data rates and offers lower latency. When designing antennas for millimeter wave frequencies, a variety of techniques can be employed to enhance gain. Some of those are frequency selective surface superstrate, radial phase gradient metalens, Bouty antenna with metamaterial array with having high refractive index, multiple input, multiple output with circular split ring resonator, MIMO employing split ring resonator based metasurface. The above mentioned techniques provide a comprehensive study of gain enhancement in both single and multi-layered mediums, but their applicability is restricted to linear polarization scenarios. The gain is enhanced by employing a uniform partially reflecting surface superstrate and a PRS using a uniform dielectric slab on top of the radiator, a wideband CP slotted patch with square ring metamaterial structure, a square metallic metasurface with MIMO configuration, end fire dipole arrays with non-uniform circular patches and cross-slot metasurface, a two-layer substrate integrated waveguide based metasurface structures are employed for millimeter waves in CP-based antennas, which mainly suffer from drawbacks such as complicated fabrication process, a more number of unit cells in metasurface, and an increased antenna profile. The proposed design utilizes a metasurface based approach to achieve high gain for the 28 GHz millimeter wave frequency range. The suggested design is unique because it presents a challenge in achieving high gain and CP at millimeter wave frequency while maintaining compact size. A single patch can achieve a gain of 6 dB. In order to enhance the signal reception over the CP antenna, a circular shaped unit cell based metasurface layer is mounted. When compared to alternative patch designs such as square, triangular, and rectangular, a circular shaped unit cell offers the benefit of minimizing the impact of losses such as scattering and edge diffraction at millimeter wave frequencies. The metasurface recommended as improved the radiation efficiency at 28.6 GHz to above 80%, resulting in a total gain of the antenna of 11.5 dBic. The proposed design is characterized by its compact size, features such as CP and high gain, making it highly suitable for millimeter wave wireless application. The paper is organized as introduction, proposed antenna design, results and discussion, and the conclusion. The proposed structure of the antenna is depicted in figure 1. And the patch antenna is fabricated on a Rogers Durite 5880 substrate material with identical properties such as dielectric constant of 2.2 and a dissipation factor of 0.0009 with a thickness of substrate as 0.252 millimeter. You can see the 3x3 metasurface patch antenna with patch antenna and a proposed antenna in the figure 1, and that antenna has a overall size of 12 cross 12 into 2.26 millimeter cube, which is nothing but equivalent to 1.1 into 1.1 into 0.2 lambda naught, where lambda naught is the center frequency. And the dimension of the patch antenna is mentioned here. And the CST microwave studio is used to simulate the design analysis. The parameters of antenna design are calculated by the above denoted formulas, where FR is the frequency, A is the truncation length, which has been mainly used for truncating the corners of the patch antenna to generate the CP. And the metasurface unit cell, which is a circular shape, is etched onto the substrate top and bottom surfaces, which is having a width and length of 4 millimeter and a radius of 1.9 millimeter and a thickness of 0.01 millimeter. And two wave guiding ports are on the opposite sides of the unit cell, while periodic boundary conditions are applied in the remaining direction, as you can see in the diagram, where waveguide ports is applied on both sides of the unit cell, and the equivalent schematics of the unit cell is represented with respect to L and C, and the S11 and S21 reflection coefficient is represented with respect to the diagram. And the effect of metasurface with and without metasurface on S11 and realized gain is depicted in the above picture, where we can clearly see that the before the metasurface, the gain of the patch antenna was 6 dBic. After implementing the metasurface of the patch antenna, which is having a gain of 11.5 dBic, and this is the entire process which has been used while designing the metasurface inspired antenna. Then this is the flow chart of the proposed design, which is depicted in figure 5. And the parametric analysis of various heights, the effect of various height between the patch and the metasurface with respect to S11, gain and axial ratio is depicted in figure 6. In results and discussion, a photolithographic fabrication method is used to validate the proposed metasurface based prototype, where a 50 ohm K type connector with a 2.92 millimeter size is attached to the patch, and a proper cavity gap between the metasurface and the patch is established employing thin plastic rods. An ionic chamber is used for far field measurement, and the proposed antenna is tested as the receiving antenna and a standard gain horn antenna with SGS series with proper calibration is used as the transmitting antenna. The test antenna was rotated to measure the radiation intensity at various orientations, and amplifiers were used to provide the stable power reception. And this is the fabricated model of the fabric proposed design, where you can see the patch antenna, metasurface, and figure C, which includes metasurface on the top of the patch antenna. In the results and discussion, figure 8 depicts the S11 experimental results, which has been compared with respect to simulation results. The S11 experimental results is measured using a Rode and Squads ZBA40 network analyzer, where and the measurement is obtained in an open air environment, which ranges the frequency range from 28.23 to 30.01 gigahertz frequency range. And figure 9 depicts the actual ratio and the gain of experimental results in comparison with respect to the simulated results. The impedance bandwidth if is the impedance bandwidth of 28.45 to 28.88 gigahertz is obtained with respect to AR, and you can see the gain from 9.5 to 11.5 dBic, and the radiation pattern is right and circularly polarized, and the cross polarization level of more than minus 20 dB is achieved with respect to co-polarization level. And table 1 depicts the comparison of existing literature in relation to the proposed work. And the proposed design is compact, which is having 1.1 into 1.1 into 0.2 lambda naught width, and it uses a similar substrate material with same thickness of metasurface and primary patch antenna. However, the air performance is little bit deteriorates due to loading of metasurface, and an additional strategies can be incorporated in the metasurface design to increase the bandwidth in the future. And finally, conclusion. The proposed design has demonstrated the effectiveness of metasurface based high gain compact circularly polarized antenna for millimeter wave application. And the experimentally measured impedance bandwidth ranges from 28.23 to 30.01 gigahertz for S11, and actual ratio bandwidth ranges from 28.45 to 28.88 gigahertz. And the design antenna achieves a peak gain of 11.5 dBic. The radiation efficiency is achieved more than 80%. Future work will be focused on improving the operational axial ratio bandwidth and exploring additional applications in emerging wireless communication technologies. Finally, the author would like to acknowledge the Rogers Corporation for providing the substrate materials needed for fabricating the prototype antennas. And these are the references which is being used while designing and studying the antenna. And this is the biographies of the author. Corresponding authors are Yerriswamy, 30, Puneeth Kumar, Tharehalli, Rajanna, and Shambulinga, Mudukavvanavar. Finally, I would like to thank the Indonesian Journal for providing an opportunity to present my paper. Thank you.